So other than the mass conservation, let's look at a little bit also on the physics and the mathematics of momentum conservation. You can derive the momentum conservation in a variety of different ways. So let's actually today try to do it in the simplest way possible. That's just following Newton's second law. So F equal to ma. All right. Now, F equal to ma works usually for a well-defined object that has a mass of m. In our case, the fluid is everywhere, right? So we don't really have a well-defined object that's called the fluid or the air. So instead of F equal to ma, we usually divide all of these by the volume. And we basically look at a very small particle fluid or a very small kind of area of fluid in this case. And V is the volume of the fluid. So this is usually how we do it. And the unit amount of force per volume is denoted as small f. And ma, m divided by v is what? Is density of the fluid. So F equal to rho A is the usual way of basically posing the fluid. And A is the acceleration of the fluid particle. And if you've looked into the exchange of Eulerian derivative and a Lagrangian derivative, so the A is the Lagrangian derivative of velocity, usually denoted as big D. That can be written as partial V partial T, the Eulerian derivative, which is equal to 0 if we are looking at a steady state flow field, plus what we call the material derivative, basically. Well, here, let me just write this in full vector form, the big V, plus a big V dot with the gradient of V. So let's look at this term later. So this first term is equal to 0, and we only have the second term that is equal to F. And in our case, the only force that's acting on the flow is the pressure force. That's minus of the gradient of not rho, but P. So that's where the pressure first comes into the aerodynamics. Okay, so let's take a look at this term a little bit more. So the equation we ended up deriving is V dot with grad V equal to minus grad P. And what is this? This is a little bit hard to conceptualize in the beginning. So let me just give you a little bit more physical illustration of what this is. So let's first of all write this out in full form, basically try to get rid of this nabla operator. This is really Ux times partial x. So I could actually let's actually look at this parenthesis, what this means. This means Ux times partial x. Well, Ux is U, sorry. Let me just write it in a little bit more simpler form. Plus V times partial y. So that is what V dot nabla means. Okay. This is equal to minus grad P. Now let's also write these two vectors into its component form. So the first component is going to be U ddx of U plus V ddy of V equal to minus d dx of P. The second component is U d dx of V plus V d dy of sorry, this is u, right? So everything on the first component is u. The second component, we are basically replacing this vector v by the second component of the vector v, which is small v. And we are also putting the second component of the nabla, which is the y derivative of p. Okay, what this is saying is that the directional derivative of u along the velocity vector direction is equal to the minus x derivative of p, is equal to the pressure force. Okay, so basically we are trying to interpret this operator here. This operator is u times ddx plus v times ddy. So if you look at the flow here, where the flow vector is like this, we have two components. We have the u component, we have the v component. This operator is the u component times the x derivative plus the v component times the y derivative. It is looking at how much the flow field has changed as you move from this point to this point, plus how much the flow field has changed as you moved from this point to this point. The total effect, if you add them together, is therefore how much the flow field has changed as you move from this point to this point where the flow is traveling towards. Right? So this green box here is really the rate of change as you move along the velocity direction at the speed of the velocity. Right, so it's essentially, let's look at another point. It's essentially comparing the velocity here against the velocity here. If this is the velocity vector, how much the flow has changed from this point to that point. And the momentum conservation equation is basically saying that the change of velocity along the velocity direction is equal to the minus of the gradient of pressure, right?